we are starting our next section of the chapter here. I'm going to talk to you at the end of class. We are starting our next section of the chapter. And we are working through, we're going to start actually building confidence intervals. As opposed to we were talking about the theory behind it and some of the interpretations about what the numbers told us. Now we're going to put that all together and start actually making a confidence interval and doing the calculations and working through the formulas. We're going to start with proportions. And then we'll go on to talking about means. And so as we look forward through most of today, the activity that they're going to be talking about is going to be this activity here, which is that we have a container full of beads, and we want to estimate the proportion of red beads in the container. All right, so that's the parameter that we're estimating, how many red beads are in the jar. And how we're going to do that is we're going to take some simple random samples of beads from the jar and see how many red beads are in that sample. So that's the example that we're going to be building from today. I do not have a jar of beads to actually do this. So we're not going to actually do the activity. But that's what this example for the next like 4 or 5 slides, that's what this example is going to be based on. So we are estimating a parameter, P, which is going to be the actual proportion of beads in the jar that are red. That's our population parameter. We're using P instead of P hat because we're talking about the population. All right, let's keep going here. Let's say we took a sample of 251 beads, and what we came up with was that 107 of them were red, the others were not red. So that means our P hat that we get from the sample is 107 out of 251. And so that is what we called, if you remembered from the first section, that's what we called our point estimate. And so we're going to start using our data here and our formulas to actually make this confidence interval. So how are we going to do that? Well, first of all, we need to check that we can use a normal distribution. Usually we do that by testing. For proportions, we did this by testing n times p and n times 1 minus p. Well, this time, instead of using p, we're going to use p hat because we don't know what the population proportion actually is. So that's what we're trying to estimate. So we're going to use the sample proportion, p hat, as our estimator. And here, our n times p hat and n times 1 minus p hat are the number of successes and number of failures. How many times were they red? How many times were they not red? The mean is the proportion. The standard deviation is the square root of pq over n. The square root of p times 1 minus p over n. Once again, we don't actually know what p is. So in this formula for standard deviation, instead of using p, we're going to use p hat. So to find a standard deviation, it would be the square root of 0.426 times 1 minus 0.426 over n, which is 251. That's our total sample size. Remember that standard deviation formula that we're using is going to end up being called the standard error. So this is saying what I said earlier. We don't actually know what P is, so we're going to use P hat in place of our actual proportions. So I had said at the end of Friday that we are going to test 3 different conditions here. We are going to check whether the 3 conditions we're going to check is random, normal, and independent. So with random, we're checking to see, did we take a random sample of all the beads in the jar? Yes, that's what we did. We took a simple random sample. Normal. We'd usually check n times p and n times 1 minus p, but now it's going to be p hat. So if we were to check those, here's n times p hat, here's n times 1 minus p hat. We get 107 and 144, and both of those are at least 10. So we can use an approximately normal distribution. And then independent, we take our sample size and multiply it by 10 and say, is the population larger than that? And I reveal that there are 3,000 beads in the container, which is greater than 10 times the sample size. Therefore, we can assume independence. So while we're writing down here, let me walk through this. I walked through this at the end of Friday. Let me walk through it again. And I'll walk through it a third time when we get to that slide in the notes. When it asks you to construct a confidence interval, they're generally asking you to go through 4 different steps. They're looking for 4 different things in your writing out of the interval. First off, you're going to state out what proportion or thing we're trying to estimate. So in this case, you would say, we're estimating P, the proportion of red beads in the jar. Then, before we do our calculations, we need to make sure that those calculations are valid, so we're going to check these conditions, random, normal, independent. That's going to be step 2. So this process that you see up here is step 2 in the problem. Step 3 is to actually do the confidence interval, do the calculation, which is what you're about to see. You're about to see how the formulas are going to work. And then step 4, we're going to interpret the interval once we have the answer. So what does the answer tell us? And that's what we practiced a little bit of in the first section at the beginning of the chapter. That's what we did in like the first day, is I gave you the confidence interval and I asked you interpret the interval. And this process we're going to use for like the next 4 chapters. So it's going to be drilled into your head by the time we've been through enough of these problems.
What does the 10% condition prove?
So question was asking about the 10% condition. Remember, the 10% condition is about independence. And I talked about, there's been a couple times back in the notes where I've talked about the 10% condition. But remember, the idea is that the bigger chunk of the population I sample, because I'm sampling without replacement, the less I can assume independence. Because the answer is going to be slightly different because we're sampling without replacement. So the probability of selecting a red bead, every time I take a red bead out of the jar, or a bead out of the jar, the probability changes ever so slightly. But not large enough to actually have an impact on the final answer, as long as I'm not sampling too much of the population. And so that's what the 10% is our cap for. If I sample too much more, then the answer for the actual probability is going to become different enough that it'll actually impact the answer. So it's saying we're assuming these things, normality and independence, and saying that it's valid to use those calculations, even though they're not exactly correct. They're going to be close enough to what the actual calculation would be that we can use them, and that'll make the problem a lot easier. So what we're checking is, are those calculations going to be close enough to the correct answer? That's what we're looking for. All right, I'm going to breeze over this next slide because I've already talked about it a couple times. I've pointed out to death that standard error is the standard deviation, whatever standard deviation formula is. Everything that comes after the plus or minus in my formula is going to be the margin of error. So the very broad scope of the formula is going to be my point estimate, my p hat, plus or minus the margin of error. And what the margin of error consists of is a critical value, a z-score, depending on the confidence interval I'm making, times whatever standard deviation formula I'm using. And that standard deviation formula is going to be called the standard error. And what are we going to use? We're going to use standard deviation formula. Since we don't know p, we're going to use p hat instead. So that standard deviation formula is called the standard error. So let's actually walk through what that is going to be. So first of all, what was p hat again? P hat was what? The proportion that were red. I'm looking for a number. It should have been listed earlier. 0.426? Okay, so when we go to do the standard error, the standard deviation, formula is going to be a square root of p hat times 1 minus p hat over n. That's going to be the standard deviation formula. And here, p hat was 0.426 times 1 minus 0.426 over, what was n? How many beads were in our sample in total? 251. So this will be our standard error. So we already know how to get standard error because we've been doing standard deviation formulas like this for a while. We did a whole bunch of them in the last chapter. But the next question then is, what is this critical value and how are we going to get it? So that's what we're going to talk about next. We're going to use a normal curve. So let's say we want a 95% confidence interval. That means we want to know what the middle 95% of the data is going to end up being. And some of it's already there for you, but if we want the middle 95%, then that leaves, for the two tails that are on the end, that leaves 5% in total for the two tails. And normal distribution is symmetric, so that means 2.5% on either side. 2.5% apiece will be a total of 5% for both of the tails combined. What that means is that a 95% confidence interval is not at the 95th percentile. Because remember, percentile deals with all of the area to the left. And so all of the area to the left will be the 95% here plus the 2.5% that's on this left tail. So if you're wanting to get what the z-score is going to be, that critical value, then you need to take the 97.5th percentile. And that's going to end up being 1.96. And so on your calculator, have your calculator out. On the calculator, if we have a certain percentile and we're trying to get the z-score, remember that that's going to be inverse norm. Inverse norm. So just to show you what that's going to look like. I want inverse norm, so I want the distribution. And instead of normal CDF, which we've been doing a lot of because we're given specific values and we want the percentage, now we're given the percentage that we want and asking for the z-score. Area, 0.975. Because we want the 95 in the middle plus that 2.5% on the left tail, so 0.975. Mean is 0, standard deviation of 1 for the z-score. 1.9599. So we're going to use 1.96. And this is the most common score you're going to need. So my guess is that a lot of you are just going to be able to memorize the 1.96. Probably by the end of this chapter. But you don't need to memorize it. If you need to do the inverse norm, that's fine. So, with that knowledge, do this for an 80% confidence interval. I'll give you a minute. Remember, the decimal you're going to put in is not 0.8. That's only the middle. You need to also factor in what you want for that left tail. Make sure you write down what you're putting in the calculator so that you remember how you did this. And it might be good to draw a picture of this curve as well. Normal distribution, we want the middle 80%. So middle 80% leaves 20% for the tails. That's 10% per tail. So if I want the percentile at this value here, I want the percentile at this value, I want everything to the left of it. Which means I want the 80% that's in the middle and the 10% that's in the left-hand tail, which means I want a total of 0.9. So your inverse norm should be 0.9. And it should be something close to -1 or to 1.28. We're going to use the positive. Critical value for an 80% confidence interval is going to be 1.28. Anyone have trouble getting the 1.28 before we go on? Good. Good. I'd draw the picture and I'd write down what you put in the calculator. All right. Here comes filling in the gaps here. There's the formula. It's not on your paper right now, so write it down on your paper. It goes here and here. You're writing it down twice. Let's talk about how it connects. P hat is my point estimate. It's my statistic. All of the formulas for confidence intervals that we're going to do are going to fit into this template. So what you're going to get on the AP test is you're going to get the building blocks for the formula, and then you're going to get the general template, this thing, that you didn't write down. It was already in front of you. And it's going to be up to you to say, oh, we're testing for proportions, so I need to fill in these pieces. Statistic, well, that's going to be p hat since this is a proportion. Critical value, that's just the z-score. Times the standard deviation of the statistic. Well, for proportions, this is my standard deviation formula. So these formulas are going to look complicated, but they're just going to be putting together a whole bunch of other formulas that we already know. And kind of combining them together. So let's actually do this calculation for my beads. We've already done most of the calculations that we need. All right. Calculate and interpret a 90% confidence interval. So if we were actually doing a 4-step process, we've already talked about step 1, where we state that we're using a 90% confidence interval to estimate the actual proportion of beads in the container that are read. We'd write out that sentence. Then we'd check that all the conditions, random, normal, and independent, are good to go. Well, we already did that. Now we're going to do steps 3 and 4. This is the calculation and interpreting. These steps are going to be on the next slide, by the way. So we'll talk about them again. But these are steps 3 and 4. Here we go. 90% confidence interval. Double check on the calculator that you can get the 1.645. Double check that on the calculator. That's going to be your critical value. We've done 95%, we've done 80%. Now this is 90%. So that means what goes in the inverse norm? I want that one answered. What goes in the inverse norm? We got 90% in the middle. It's going to be 0.95 because then we got the 5% on each tail. So we got the 90% that's in the middle, and then we have the 5% that's on the left tail. So it's going to be inverse norm of 0.95, which should give you the 1.645. So now let's fill in all the pieces. Here they come. There's the template. What's the statistic? It's p hat. It's this thing. Plus or minus. Stop writing for just a second. Let me break down so that you understand what you're writing, what you're about to write down, because it's going to be a long string of decimals. I want to make sure you understand all of it. Statistic, that's p hat here. Plus or minus. Critical value, that's my z-score here, the 1.645. Times the standard deviation of the statistic. That's this. We're using p hat instead of p because we don't know what p is. And so it's going to be my 0.426 plus or minus my critical value, the z-score, times that standard deviation formula. There it is. I will not make you plug all this in the calculator. I will just tell you that all these come out to be plus or minus, it's going to be 0.051, so that's going to be your confidence interval. And then there's 2 separate questions being asked. It asks you to interpret the interval. So what does this tell you? And then it asks the question, if I say that half the beads are red, what do you think about that claim based on the confidence interval? What is that confidence interval telling you about this idea that p is actually 0.5? I'll let you finish writing down, and then we'll talk through the rest of it. Ready? We're mostly ready. All right. Confidence interval, the interpretation, always starts with, we are 90% confident that the actual parameter, which was what? It was the proportion of, so the proportion of the beads there that were red out of all of them. So we're 90% confident that the proportion of the beads that were red falls between these two numbers. So these are my plausible values that I think could be the actual proportion. Does that include 0.5? No. So what do we think about that claim? Well, maybe it's not the case. There they are. Let me jump for just a second to say that you're going to have a new homework assignment. I'll post it on Canvas while you finish writing this down.